All right, good afternoon, evening, or morning, ladies and gentlemen. Welcome back to yet another episode of CS341 Algorithms. And today, in our 20th lecture, we're going to be wrapping up the traveling salesperson reduction that I didn't cover last time. And then we're going to be talking about a new complexity class, non-deterministic polytime, or NP. And before I jump into the material for today, I have one announcement. So the course evaluations have opened, and they're going to be open until April 3rd. So if you have a moment, I'd ask you to please head over to evaluate.uwaterloo.ca and submit an evaluation for the course there. This would be super helpful for us instructors. Especially those of us who are eventually going to be going up for tenure, having a good response rate for evaluations is very helpful for us. So please go there and submit your honest and constructive feedback, and we'd be super interested to hear what you guys have to say. One request, though, the purpose of the evaluation is to evaluate the instruction in particular and not extenuating circumstances like how COVID-19 has been handled by the school or by the instructors. So if you could try to limit your comments and your sort of divorce your perception of the course from how COVID-19 was handled, then that would be much appreciated. Okay, I won't dwell on that anymore. Please go there and submit your evaluations. Let's jump into today's material. We're going to start out by finishing up our traveling salesperson reduction that we didn't cover last time. Okay, so just to refresh your memory here, last time we talked about three different variations of the traveling salesperson problem. There was traveling salesperson optimal value, where you have a graph G and a bunch of positive integer edge weights. And the question was, out of all the possible Hamiltonian cycles in the graph, to remind you what a Hamiltonian cycle is, a Hamiltonian cycle is a cycle that visits every vertex in the graph exactly once. So it's going to be like n edges in the graph that connect n different vertices, and they have to be unique vertices. So you only visit each vertex exactly once. It's a cycle that visits each vertex exactly once, okay? And TSP optimal value asks, out of all the possible Hamiltonian cycles in this graph, consider the Hamiltonian cycle that has the smallest total edge weights, so the smallest total sum of edge weights along that cycle. We're going to call that the minimum Hamiltonian cycle, or the optimal Hamiltonian cycle. I want to know, what is the smallest total sum of edge weights? What's the smallest total weight of any Hamiltonian cycle? Return that weight. That's TSP optimal value. And last time we showed that you can reduce TSP optimal value to TSP decision. So given a constant time solution, an oracle to solve TSP decision, let me just get my cursor here. Given a constant time solution to this problem, TSP decision, an oracle that solves this problem, a TSP decision solver routine, we can actually solve TSP optimal value in polynomial time in the input. Okay, so just to refresh your memory about TSP decision, because that's what we reduced to, you take a graph and a bunch of positive edge weights, and you also take a target value t. And the question is, does there exist a Hamiltonian cycle in the graph with total weight t or less? So can we find a Hamiltonian cycle that matches this target weight t, or does better than this target weight, has a smaller target weight? And TSP decision, of course, is a decision problem. It's going to return just true or false, yes or no. Is there such a Hamiltonian cycle or not? And so given this decision problem, which sort of gives us one bit of information, is there such a cycle, yes or no, we were able to reconstruct the optimal value, the optimal weight, by doing basically a binary search on the range of possible weights for Hamiltonian cycles. Okay, this time we're going to ask, can we reduce TSP optimization? What's TSP optimization? We take, as before, a graph and positive edge weights, and we're trying to find not just the optimal value of the optimal weight of a minimum Hamiltonian cycle, but actually give me a minimum Hamiltonian cycle. Give me an optimal Hamiltonian cycle. Output the entire cycle. What does this mean? Really, it means outputting the set of edges on some optimal minimum weight Hamiltonian cycle. So somehow we want to return the actual minimum Hamiltonian cycle, or a minimum Hamiltonian cycle if there are multiple. And we want to reduce this problem to just this decision problem where we kind of only get this single bit of information per call to the oracle. So we want to be able to reconstruct from these decision problem calls what the actual minimum Hamiltonian cycle is. Okay, and this might seem kind of hard, but we'll put together a solution here, a reduction. Okay, let's start to think about this. So first of all, we saw last time how to get the weight T star of the minimum Hamiltonian cycle, right? And so if we reduce, getting the actual optimal value, that weight of the minimum Hamiltonian cycle to TSP decision, then, okay, we can solve for the minimum weight of a Hamiltonian cycle. So we can get that. We can get T star. And then if we take T star and we start to invoke TSP decision, passing T star as the target, we're passing the optimal weight as the target, we can start to ask questions of the oracle of the form, does there exist a Hamiltonian cycle H in G with optimal weight? So we can ask questions, true or false, about the existence of a Hamiltonian cycle with optimal weight. Okay? Now what can we do if we ask questions about the existence of a Hamiltonian cycle with optimal weight that'll help us sort of figure out which edges are involved in a Hamiltonian cycle of optimal weight? Okay, so if you want, you can pause and think about that for a moment. I'm going to assume you've done that if you wanted to think about that yourself. So here's sort of an interesting idea. What if we run a little experiment where we take the graph G and we want to answer the question, is some edge E involved in the minimum Hamiltonian cycle? Here's an idea. What if we delete the edge E and then we call TSP decision with this optimal weight T star? If TSP decision returns true, then we've learned something kind of interesting. So you might want to pause and think, what? What we've learned is that if we remove this edge, we can still find a minimum Hamiltonian cycle. So there is a minimum Hamiltonian cycle that doesn't use this edge. So we might as well delete this edge. We might be pruning down the number of optimal Hamiltonian cycles there are, but we aren't removing all Hamiltonian cycles of optimal weight. We can still find one if we continue the process. But now we've removed an edge, so we're sort of progressing towards, a solution where the number of edges in the graph is just the number of edges on that Hamiltonian cycle, or the set of edges in the graph is just the set of edges on a minimum Hamiltonian cycle. So that's the idea. We're going to try to delete edges to progress towards a state where we just have exactly a minimum Hamiltonian cycle in the graph. Okay, so that was if TSP decision returned true. What if TSP decision returns false? Well, in that case, there is no minimum Hamiltonian cycle, or sorry, there is no instance of a Hamiltonian cycle with this minimum weight T star in the graph anymore. By removing this edge E, we removed all of those Hamiltonian cycles that achieved weight T star. Well, okay, that's bad. We don't want to remove all of those optimal Hamiltonian cycles. We want to find one of those. We want to return it. So if removing an edge removes all of those optimal Hamiltonian cycles, well, that means that edge is on every optimal Hamiltonian cycle. Okay, well, that means if I include that edge, I've actually included an edge that's on every optimal Hamiltonian cycle. So, at the end, if I keep all the edges that are part of every Hamiltonian cycle, and I remove the edges that are not part of every Hamiltonian cycle, my claim is I'm going to end up in the end with the graph being exactly a Hamiltonian cycle. Okay, so that's the claim. Let me try to show you the algorithm here. So we're going to start out, here's our TSP optimization solver. We're going to take a graph G equal to VE and some weights as input, and we're going to have these external oracle we're assuming. TSP decision solver is an oracle we're assuming exists, and I'm also, just for simplicity here, assuming that TSP optimal value solver exists as an oracle, but this doesn't mean I'm not actually reducing to TSP decision. This doesn't mean I'm reducing to like multiple oracles, because if you remember last time, TSP optimal value solver is reducible to TSP decision solver. So this can be done from TSP decision solver in polynomial time that's polynomial in the input size. So if we wanted to rewrite this code to remove any dependence on the TSP optimal value solver we sort of introduced last time to make this a pure reduction to a single external oracle, then we could just take this TSP optimal value solver code and like inline the pseudocode that we wrote last time, which was all in terms of TSP decision solver, okay? But this is in polynomial time in the input going to compute the actual optimal weight, for the minimal Hamiltonian cycle, minimum Hamiltonian cycle. So T star is that optimal weight. We're going to compute this in poly time. And now if that optimal weight is infinity, what does that mean? That means there's no Hamiltonian cycle in the graph at all. So in that case, we should definitely just return no Hamiltonian cycle exists. This is an if and only if, right? Because the only way that T star is infinity is if there's no Hamiltonian cycle. Okay? So this sort of suggests we're going to return here if and only if there's no Hamiltonian cycle in the graph. And then we're going to sort of try deleting edges one by one, and we're going to keep an edge if deleting it removes all the optimal Hamiltonian cycles. And otherwise, if we can still achieve an optimal Hamiltonian cycle removing an edge, then we'll remove that edge. And so we're going to need sort of like a mutable copy of the graph. So what I'm going to do is I'm going to take this weight array. Let's just assume it's a weight matrix. Well, actually, it doesn't really matter. It'll matter once we start to talk about runtime, but it doesn't really matter what the representation is right now. We're just going to copy all of the weights, copy the weight function in whatever form it is. Maybe it's a matrix, maybe it's an array with one slot per edge. I don't know, doesn't matter. We're going to copy whatever it is, make a duplicate W0. Okay, and then H is actually going to explicitly contain the set of edges that are part of the minimum Hamiltonian cycle that we're going to construct. Okay, we'll argue at the end. We're going to return H. We'll argue at the end that the H that we've returned is precisely the minimum Hamiltonian cycle. Okay, so how does this work? Well, for every edge, we're going to try setting that edge to infinity, the weight of that edge to infinity, which is effectively deleting the edge from the graph, right? And then we're going to call TSP decision solver on the graph with this modified weight function, where edge E has been deleted. Now we're going to give it this optimal weight, optimal total weight for a Hamiltonian cycle to try to match or beat. And if it can't match or beat T star, the optimal weight of a Hamiltonian cycle, then that means by deleting edge E, we removed all optimal Hamiltonian cycles of this weight. So that means it was a mistake to remove this weight. We should add this weight back in. Okay, so we set the weight of E back to the original weight of E. We set the weight of E in our copy W0 back to the original weight. We restore that edge. And now, when we're restoring that edge, what are we saying? We're saying it's a bad idea to remove that because that removes every optimal Hamiltonian cycle. So this edge is part of every optimal Hamiltonian cycle. So whatever Hamiltonian cycle we're going to return in H, this edge, whatever optimal Hamiltonian cycle we're going to return in the end as H, that Hamiltonian cycle is going to include E. So we can add it to H. It's going to be part of every optimal Hamiltonian cycle. Okay, so we add it to H. And now, so this is all stuff that I just said. My claim is, at the end of this loop, the graph is going to contain precisely the edges that are part of every minimum Hamiltonian cycle, and then we're going to prove that H is exactly the singular, or a singular, minimum Hamiltonian cycle. Okay, so there might be other minimum Hamiltonian cycles in the graph, but H is going to be exactly one minimum Hamiltonian cycle, so it's the correct thing to return. We're getting back a Hamiltonian cycle of optimal total weight. Okay, so let's think about the correctness a little bit here. The way I'm going to break this down is we have a loop invariant. Okay, so here's the loop invariant. There exists a Hamiltonian cycle of optimal weight T star in the graph induced by the weights W0. So consider the set of weights, or the matrix or whatever of weights, the weight function W0. Consider all the edges that are defined in there because they're finite. Okay, so infinities are undefined. They're edges that don't exist. So consider all the finite edges. Those edges induce a graph. The claim is there is a Hamiltonian cycle of optimal weight T star in that graph. Okay, so let's argue that. So first of all, that loop invariant is true before we enter the loop, right? Because if we get past this line where we would return no Hamiltonian cycle exists, we get past here because T star is finite, and the fact that TSP optimal value returned a finite number T star means there is a Hamiltonian cycle in the original graph with total weight T star. And W0, initially we copy W, so W0 represents the original graph. Okay, so this is true. The graph induced by W's by the finite edge weights in W0 does contain a Hamiltonian cycle of optimal weight T star before we enter the loop. So at the beginning of our first loop iteration, this is true, the loop invariant holds. We need to show that if we assume the loop invariant holds at the beginning of an iteration of the loop invariant still holds at the end of that iteration. So let's do that. Let's assume it holds at the beginning of an iteration. Then we set some edge to have weight infinity. So we may have removed all Hamiltonian cycles of weight T star in W0, in the graph induced by W0. But if that happens, then TSP decision solver will return false. And if it returns false, we will actually restore that edge weight, and we'll restore the graph to the state it was in at the beginning of this loop iteration. And at the beginning of this loop iteration, we knew there was a Hamiltonian cycle of weight T star in the graph induced by W naught. Okay, so if we remove all Hamiltonian cycles of optimal weight, then we're going to put all of those cycles of optimal weight, Hamiltonian cycles of optimal weight, back before we terminate the loop iteration. And if we call TSP decision solver and it returns true, so that we keep this edge weight at infinity, the fact that TSP decision solver returns true tells us there's still a Hamiltonian cycle of optimal weight T star in the graph induced by W0 at the end of our loop iteration. Okay, so that's a proof of the loop invariant. Now what can we do with this loop invariant? Well, by the end of the loop, notice that when do we add an edge to h? We add an edge to h precisely when we set it back from infinity to a finite number. So if you think about what we're doing with every edge in the graph, for each edge in the graph, we're taking that edge, we're setting its weight to infinity, and it's either staying infinity if TSP decision solver returns true, or it's being set back to a finite number and being added to h. So as we go, we're either throwing out an edge, setting it to infinity, or we're adding it to h. So at the end of the loop, h is going to contain precisely the finite edges in W naught. And we argued at the end of the final loop iteration, the loop invariant will hold. So there will be a Hamiltonian cycle of weight T star in the graph induced by W naught, induced by the finite edges in W naught. And H will contain all of those finite edges in W naught. So there will be a Hamiltonian cycle of optimal weight in H at the end of the loop. Okay, so H will contain a Hamiltonian cycle of optimal weight. That's not the same as saying H will contain precisely a Hamiltonian cycle of optimal weight. Okay, there might be some extra stuff in H. So there is a Hamiltonian cycle C of optimal weight contained in H, but there might be some extra edges. Well, what if there are some extra edges in H? And here I'm going to draw this out, this part of the proof. I'm going to draw out a diagram for you here on the right, so you can sort of see an example. Of course, I'm not proving this for this specific graph. I'm proving this generally, right? But you can see an example graph, so kind of all the steps of the proof are demonstrated visually for you, and you can understand that they actually apply to a general graph. Okay, so at the end of the algorithm, there's a Hamiltonian cycle C of optimal weight T star contained in H. Okay, so here's our Hamiltonian cycle C of weight T star. It's contained in H, and maybe there's some extra edges in H. Okay, if there are no extra edges in H, if H is precisely C, then we're done. We can return H, and we'll be returning precisely a Hamiltonian cycle of weight T star, optimal weight T star. So let's suppose not to obtain a contradiction. Well, then H must contain some extra edges. So consider some edge E that's an extra edge beyond C. Okay, so in addition to C, there's some extra edges. Let E be one of those extra edges. Consider the iteration when E was considered. Okay, remember our algorithm considers edges in iterations of that loop, right? We loop over all the edges. And in each step, we either remove an edge or keep it, right? And at the end, the claim is H contains E at the end, so E was not removed in the iteration where it was considered. Okay, let G prime be the state of the graph at the time when E was considered. So remember, we're removing edges as we go, and G prime is the state of the graph at some earlier time when we considered E. Okay, at that time, maybe E was the last edge we considered, and G prime is actually just the same as H. Or maybe G prime is a much earlier time, and maybe there are some extra edges in graph G prime. So I've drawn these here, right? We have potentially some extra edges in G prime. The point is, we're just removing edges over time, so H is going to be a subset of G prime. Okay, and remember, C is part of H. So that means C is a subset of G prime. Okay? Now, since the algorithm does not remove E in this iteration, because E makes it all the way until the final iteration and it's in H at the end, so E does not get removed. Now, what's the situation where our algorithm doesn't remove E? It doesn't remove E if removing E would remove all Hamiltonian cycles of optimal weight T star in G prime. Well, in particular, if it removes all Hamiltonian cycles of weight T star, it must remove C. So removing E would remove C from G prime. And now we're getting close to our contradiction, because E is not part of C by our assumption. So we start with C being in G prime, and then we remove E. Well, it's not part of C. So C is still going to be in G prime. Well, that's a contradiction, because if the algorithm didn't remove E, it must be because removing E would remove all of the Hamiltonian cycles of weight T star, including C. But it can't remove C because E is not part of C. Okay, so that's a contradiction. So what does this contradiction get us? Well, our assumption must be incorrect. The only assumption we've made is that H is not precisely a minimum weight Hamiltonian cycle C. Okay, that assumption has to be wrong. So H has to be precisely a minimum weight Hamiltonian cycle C. Okay, so that tells us this is a correct reduction. H that we're returning is precisely a minimum weight Hamiltonian cycle. But is it a polytime reduction? Okay, so we of course talked about this a little bit last time, right? So how do we approach this problem of showing that this is a polytime reduction? Well, we need to ask what's the size of the input and what's our runtime. And when it comes to the size of the input, we kind of have to ask ourselves what's a reasonable representation, right? We shouldn't pick a representation for the input that's exponentially larger than an optimal representation of the input. Okay, and I'm not requiring you to know exactly what an optimal representation of the input is, but you can look at the table I gave last time and get at least some intuitive idea of what's reasonable and what's exponentially too large. I give a bunch of examples of representations that are exponentially too large. Okay, so let's pick what I consider to be a reasonable adjacency matrix representation for V and E, and a weight matrix representation for W. Okay, so adjacency matrix representation for the graph, weight matrix representation for the edge weights, and let's just assume that it takes O of 1 time to read, write, or do arithmetic operations on weights, and that each weight takes O of 1 space, okay? So this is a relatively simple assumption that you're all used to. This is just the unit cost model. Weights fit into a single word of memory, and we're under the unit cost model. Now, sometimes we don't work on the unit cost model, right? And we get like log weight terms would start showing up. We'll consider what happens if we did that shortly. The preview is it won't actually change the answer to the question, is this a polynomial time reduction, in most cases. In most cases, it won't change the answer to that question. Okay, so what is size of I then? Well, if we have an adjacency matrix representation for V and E, that's going to be basically order V squared, order N squared, right? Space to store that adjacency matrix. And then the weight matrix, if we assume O of 1 space for each weight, then it's just for each U and V in V, we have a weight written down. Okay, and some of those weights might be infinity, but we're just assuming that we can fit, an infinity or any positive integer weight in constant amount of space. And of course, infinity would really just, of course, you can't write down infinity, right? On a real system, you can't write down the number infinity, so you reserve some number like -1 or something to represent infinity. Okay, you just have to be careful. If you use a negative number like -1, you have to be careful about how you treat your infinities and comparisons and sums and things like that. Okay, but at any rate, we should be able to write down any weight in O of 1 space. So how many bits are going to be needed to write down the entire weight matrix? Well, it's the sum for all uv and v of 1. Well, this is v squared times 1. So the whole thing is cardinality v squared, or n squared, is the size of I. So the number of bits needed to write down the input, we're going to assume it's order n squared based off of this representation that we chose as a reasonable representation. Okay, now let's ask what's the runtime of this algorithm on such an input. Now let me take a sip of my tea here. Okay, so TSP optimal value solver, we argued last time that this actually runs in time polynomial in the input size. We reduce it to TSP decision solver and it runs in poly time, okay? And now this next step where we just sort of check if t star is infinity and return, if so, that's constant time. Now, yeah, I mean, in the real world, printing strings is only constant time if the length of the string is constant. It is here, just worth mentioning. W naught, we want to copy W to W naught. Okay, we're copying a matrix where each slot takes O of 1 space to read or write, and there are n squared slots, okay? So that's n squared time to copy that matrix. And then we're going to create, let's just create, and we could represent H in all different ways. Let's just represent H as like another n squared size matrix. So when we talk about adding, like adding an edge to H, we're just going to say the edge from, well, look at that edge, look at its endpoints. U and V are the endpoints of the edge. We're just going to set H of U comma V to 1. Okay, so we use like a matrix of booleans where the edge is in H. It's an adjacency matrix, really, of bits, where single bits, 1 bit per edge, where an edge is present if H, an edge from U to V is present if H of UV is 1, okay? So we'll just pick that simple adjacency matrix representation for H, so it'll take order n squared time to initialize, create and initialize that matrix. And then we're going to iterate over all the edges here. How many iterations? Well, let's just do a dumb iteration scheme where we don't try to be precise and do order m iterations. We're just going to iterate over all pairs of uv. Okay, so that'll be n squared over all nodes u and v, pairs of nodes u and v in capital V. Okay, so all pairs of nodes, n squared pairs. And then if we look at what happens in each of those loop iterations, we assign a weight to infinity, that's constant time. We call TSP decision solver, it's constant time. We assign a weight, possibly we do this then case. So we assign a weight WE to W naught of E, constant time. We add an edge to H. How long does it take to add an edge to H with this representation? Well, we look at the two endpoints of the edges, U and V. And in fact, that's explicit because we're looping for all U, for all V, right? That's our order n squared iteration. So we have U and V directly. We just set H of U comma V to 1. That's it. That's how we add it. So that takes constant time too. So the runtime is going to be polynomial in the input, some polynomial in the input size for this call, plus order n squared plus order n squared plus order n squared times order 1. That's all just some polynomial in the input size plus order n squared. Okay? Okay, so poly of size I is definitely polynomial in the input size. Does order n squared somehow ruin this algorithm, making it not polynomial in the input size? Because this first term certainly is polynomial in the input size. Is the second term also polynomial in the input size? Because if it is, we have the sum of two terms that are both polynomial in the input size. The sum of two polynomials in the input size will also be a polynomial in the input size. So let's check if O of n squared is poly in the input size. Well, the input size is order n squared. So clearly, O of n squared is in big O of 1 times the input size to the 1. That's a polynomial in the input size, right? So yes, it is, right? So this runtime is polynomial in the input size. This is a polytime reduction. We showed it's correct. We showed it runs in polytime in the input size. So this is a polytime reduction. Now here's a question. How would this change? How would this complexity or the answer to the question, is this a polytime reduction, change if we assumed that each weight actually occupied log W space? Each weight W occupied log W space, because we can write down every number from 1 to W in log W bits, right? Order log W bits. And then operations on it, because each weight takes log W space, operations on it have to at least read all of those log W bits. So in this non-unit cost model, in this bit complexity model, we would think of those operations as taking at least order log W time. So reading, writing, comparing, adding, subtracting, all of those operations on weights would take order log W time. And actually, we don't have to do any multiplication of weights here, but if we did multiplication of weights, it would end up being something like order log squared W time, okay? So if we consider this bit complexity model, do we end up with a different answer to the question, is this a polynomial time reduction? Okay, and I'm going to argue to you that we don't see a different result. Okay, so suppose that we assume order log W time for reading, writing, arithmetic operations on each weight W, and order log W space for that weight, okay? So the size is going to look different, right? Because now, for every slot in our weight matrix, we no longer have order 1, we have order log W, where W is the specific weight number written down there. So that's W u comma V. W of u comma v. Okay, so we have this log of W u comma v term here. Okay, and note that there's one of these log of W u comma v terms for each uv in v. So there are going to be sort of order v squared of these things, and if we assume that this is at least 1, then you can sort of fudge the numbers a little bit here. But this basically breaks down to just this sum. Like, this sum should end up dominating this v squared term in most cases. Maybe this analysis is not quite perfectly sound because I discard this v squared term. Let me run through it as if the v squared term is not there, and then I'll think to myself, if the v squared term were there, would that change anything? And it shouldn't. So we'll kind of make sure that everything here seems kosher in the end. Okay, so let's just assume it's not a mistake for a moment to delete this v squared term and assume that this sum term dominates. I'll tell you the reason I'm concerned about this, and I'm sort of making a fuss about this right now. You could have a graph where every weight is 1, and then the log of 1 is 0, and the sum of a whole bunch of zeros would just be 0. So this term itself might be order 0, basically, which is sort of a weird expression that I'd like to rule out. So I might not like the fact that I've deleted this v squared term here. Let's see if that matters in the rest of this argument, and if it does, I'll put it back and correct the slides. Okay, so what's the runtime on such an input? Okay, well, now that we have a different amount of space used, technically speaking, in our reduction from TSP optimal value solver, where we got the optimal value from TSP decision, we kind of have to make that argument again that that's a polytime reduction in the size of the input, because we didn't make that reduction under the assumption that there were these log W terms. Okay, so let's not do that now, because it's just kind of pedantic. I believe you could do that. Let's imagine that you just went and did that first as an earlier step. So suppose we showed already that TSP optimal value solver ran in polynomial time. Let's show that this all runs in polynomial time. Okay, so this step is constant time. This step, now we have to copy the matrix. We're going through each of the slots, and we're doing order log WUV work to copy, to read and write that, those log WUV bits for that weight WUV. And then for H, we're still creating an array with 1 slot per thread, so that's still n squared. And then we have n squared iterations for all U, for all V. And then now when we assign a weight, it's actually log WU of V. And by the way, if we have an infinity here, if WUV is infinity, log infinity is infinity, right? But we don't mean an infinite number of bits, right? Really, we actually mean that you reserve sort of 1 extra bit or 1 extra value to serve as an infinity, so that can increase the number of bits you need to represent all the numbers plus an infinity by at most 1. So it's still order log WUV, where just imagine that the infinities are actually replaced by the maximum value that's stored in any array cell, like +1 or something like that. Like they're really replaced with a -1, and in order for this log term to work out, like log -1 would give you some nasty result as well, right? So you just sort of have to imagine what's the number of values that I could possibly store in this field. If in the input, the number I store here is 100, then I need log 100 bits to write down all the possible numbers from 0 to 100. That's sort of what we're representing. If I could write down kind of 100 or infinity, then we sort of need log 101 bits to describe all the possible values from 1 to 100 plus the possible value of infinity. So anyway, this should be sort of log the number of values that can be written down in this slot. And you can imagine that infinity just, this will sort of end up being the maximum weight of any cell, something like that. The maximum weight of any edge in the graph, log maximum weight of any edge in the graph. Okay, so this call is going to be constant time because we already, we haven't actually argued to ourselves that this is constant time. In fact, oh no, sorry, my mistake. I'm confusing myself here because I went off on a tangent about the log of infinity here. This is the oracle call. We assume the oracle call is always constant time. Sorry about that. Okay, so once we get in here, we're copying WE into W0 of E. That takes log W of UV. And then this, adding to H still takes constant time because we're just sort of looking up H of UV and writing a bit. Okay, so the complexity here is going to be some, assuming that we manage to show this result, this polynomial result, complexity for optimal value solver. It's going to be some polynomial in the input size plus order the sum of all pairs over all pairs UV and V of log weight of UV, all plus n squared for this complexity. And if you're wondering, so we have this term is showing up. Right, this term for copying the matrix, that's right there. And then we have this n squared term for creating this array, and then we have n squared iterations, and in those n squared iterations, for each of those iterations, we're summing up, this O of log WUV complexity and this O of log WUV complexity. So that we just get another one of these terms, the sum for all U and V pairs in V, really in V squared, the pairs in V squared, of log WUV, right? So it's sort of, you can imagine there's a 2 in front of this sum, right? Because we have this term, and then we have this term appearing again as a result of these two for loops. Okay, but of course it disappears in the big O notation. So this is our runtime. And I've missed the poly of size I here, but I've sort of made the exact same simplification here, where I've assumed that this sum of log weights term dominates the n squared term. That's because there are n squared of these elements being summed, n squared of these terms being summed. Maybe it's questionable, as I mentioned above. If the w's are all 1, then this is questionable because it sums to 0. But anyway, I've made this same possibly erroneous simplification where I assumed that this n squared term is dominated, so I delete it, and I accidentally forgot to copy this poly of size I term here. So this should be poly of size I plus order this sum. Okay? And clearly this term is in poly of size I, where size I is this, because this term is exactly size I, right? This term order this is exactly size I, which is order of this, right? They're both, size I and this term are both in order of this sum. Okay? So clearly this term, this runtime, is poly of size I, because you have a poly of size I term and then you have this other term. Okay, so the runtime is polynomial in the size of I. Okay, so this is still a polynomial time reduction, even if we allow, if we step out of the unit cost model into the bit complexity model. Okay, now let me return to this question of whether this v squared term is dominated. I think it probably doesn't make sense to say that the v squared term is dominated by this sum, even though this sum is n squared different terms being summed up. Because each of these terms could be 0 if you just are summing the straight, log w. Okay? Now really, if you think about what these log w's represent, they represent how many bits you need to write down infinity or the value that's in that particular cell. And you're going to need at least 1 bit per slot. So really this is really supposed to be order log w, but the order is just being subsumed in this bigger big O, this outermost big O term. So this isn't really properly a sum of log w, it's a sum of some constant times log w plus some constant. And so really these terms will be at least 1, but it looks like an incorrect transformation from this step to this step, because the log w's, wuv could be 1, and then log w would be 0, and then the whole sum would be 0. So it would make me more comfortable if I didn't throw away the v squared term in this step here. And if I keep that v squared term, remember cardinality of v squared is just n squared, right? So we get n squared plus this. And again, if we kept this n squared term in the runtime, we would also have n squared plus this. So clearly, you would still get that the runtime is polynomial in the input size. So I think I'll tweak the slides to show that. And that's the preferred thing. That's the preferred way to do this. If you shouldn't throw away terms and say they're dominated if you can't argue that this term is strictly less than a constant times this term. Okay, so I'm not comfortable with crossing out this term here. You shouldn't be either, for the reasons that I just explained. Okay, so what we learned here is that the unit cost versus non-unit cost, that is, versus bit complexity assumptions, bit complexity model assumptions, they don't usually make a difference in this setting. And that's because really, when you introduce the log w space overhead for a particular variable, then accessing that variable starts to take order log that variable time, right? So if you increase a logarithmic space term, you're going to have to pay that logarithmic space term as a time term to access that variable. So usually your time ends up blowing up by sort of the same factor as your space does. And so if you would be polynomial time in the space complexity under the unit cost model, if you blow up all those terms with these sort of logs moving to the bit complexity model, you're blowing up your time and your space. So you should still end up with time that's polynomial in your space complexity. So at least intuitively, that should give you this idea that it doesn't actually make a huge difference whether you have these log terms or you don't have these log terms in this setting. Okay, so let's recap this stuff before we move on to defining the complexity class NP. So with the help of this final reduction that we just did, if you go over sort of all the different reductions we did last time and this time and just see what all the the sort of the directionality of all those reductions is. I'm reducing A to B and B to C and C to D and D to E. Check out what sort of the direction of all those reductions is, and you'll realize we end up reducing all of these 3 flavors of the traveling salesman problem in a cycle. So we sort of showed TSP optimal value reduces to TSP decision, and TSP decision reduces to TSP optimization, and TSP optimization reduces to TSP decision, and TSP decision reduces to TSP optimal value. So you end up showing that these all actually reduce to each other through some path in the reduction graph, if you will. If you make a graph where the nodes are problems and the edges are reductions, they're directed edges showing which direction the reductions are happening in, you'll find that actually the 3 different TSP flavors, problem flavors, are part of the same strongly connected component. So they are all actually equivalent in the sense that if you can solve one of them in polynomial time, you can solve all of them in polynomial time by possibly a sequence of reductions. So what this shows is these 3 flavors of traveling salesman problem are polytime equivalent. Okay? And the way that we show polytime equivalence is by we reduce problems to each other, right? So if I can show that TSP optimal value reduces to TSP decision and TSP decision reduces to TSP optimal value, then I can reduce both directions, right? So the 2 problems are polytime equivalent, right? So I have to be showing polytime reductions in order for them to be polytime equivalent, right? Okay, so as you recall, one of these was a decision problem and the other 2 were not, and so we sort of made some rough, at least intuitive argument here that the decision and non-decision flavors are polytime equivalent in this case, and my claim is that they actually are usually polytime equivalent for many different problems that have decision and non-decision flavors. You end up being able to, if you could solve the decision problem, then you could reconstruct a fairly sophisticated output for a non-decision flavor of the problem in polytime using an oracle for the decision problem. Okay, so why is this important? Well, what this suggests is we actually don't need to study the enormous diversity of possible output formats for problems. We don't necessarily need to study all sorts of non-decision flavors for problems. It suggests that we can restrict our attention to the decision flavors of problems in most cases, and know that if we study the complexity of the decision versions of problems and relate the complexities of decision versions of problems to each other, so if we express the relationship, the complexity relationship, the difficulty relationship between two problems by considering the relationship between the decision versions of those problems, that is in many cases as good as considering all of the different combinations of non-decision flavors of those problems, in the sense that it wouldn't make a difference to the question, are these problems polytime equivalent, or is there an exponential gap between these problems? Okay, and we also saw polytime Turing reductions, and we sort of got a hint of what it means to be correct. It sort of means that the return value is correct for every possible input, and we saw that part of showing that a polytime Turing reduction is a polytime Turing reduction, or your proposed algorithm is a polytime Turing reduction, is to show polytime. You should show that the runtime is polynomial in the input size, assuming a reasonable input representation. Okay, and next class, we're going to learn about a restricted class of reductions with clearer correctness guidelines, because this is sort of a slightly vague correctness guideline, right? The return value is correct for every possible input. I mean, you can show this, right? But this doesn't give you a particularly mechanical way of approaching the problem. We'll see a restricted class of reductions that have a much clearer correctness guideline, where there's a fairly mechanical approach. That'll be super useful for making it easy to prove that problems are NP complete, and we'll see what that means soon. Okay, but let's talk about the second major topic of today, which is the complexity class NP. And it's tempting, since we saw the complexity class P last time, and that stood for polytime problems. It's tempting to think that NP stands for non-polytime problems. That's not true. Okay, so P is polytime. N is also polytime, just a weird polytime. It's non-deterministic polytime. Okay? And we'll try to explain what that means. And I'm going to try to describe what NP is with a rolling example, sort of a running example of this problem called the subset sum problem. The subset sum problem. So what's this problem? Well, suppose we were given an array of integers. So here, for example, we have -7, 3, -2, 5, 8. They don't have to be sorted. I've just drawn them sorted here just to make it easier to see. And the question is there any subset of these that sums to 0? Okay, we're not looking before, the first lecture we studied the question of whether you could find a subinterval, a consecutive subinterval that sums to 0. This is a different problem. Is there any subset that sums to 0? For example, let's see, is there a subset that sums to 0? Well, it happens to be an interval here, so it's a bad example. Anyway, any subset that sums to 0. So if there were like, a 7 term over here, then this -7 plus that 7 would sum to 0. That would be fine. Okay, so in this case there is, -3 plus -2 plus 5 is 0. Let me take another sip of my tea. Now, finding such a subset can be extremely difficult. So my claim is this is actually about as hard a problem as we know how to formulate. That's not exactly true, but it's close enough. This turns out to be an NP-complete problem, if I can sort of spoil this for you. This problem is as hard as every other problem in NP. And we'll find out that the problems in NP are very hard problems. We don't know how to solve any of these problems in polynomial time. Okay, so here's an interesting question. Could I make solving this problem simpler somehow if I had some higher power, some oracle that would tell me something that would help me solve this problem? Well, what if we had an oracle give us something called a certificate? What's a certificate? Well, in this case, a certificate would, for example, consist of an array of numbers. And the oracle would claim that it represents a subset of the input that sums to 0. Okay, so the oracle could give you a certificate containing -3, -2, plus 5. Okay, so that's a certificate. It's an array of numbers, and the claim is that it represents a subset of the input that sums to 0. Now, I could be given something else. We'll talk about that in a moment. Maybe the oracle is lying to me. Okay, but if the oracle is telling the truth, then we'll call this a yes certificate. And a yes certificate is essentially a proof that yes is the correct output, right? So we have a proof right here. This is a proof that the output, if under the assumption that the oracle is telling the truth, that this is a subset of the input, and that this does sum to 0, then this set of numbers, -3, -2, 5, that's a 3-element set that is a proof that yes is the correct output. How would I check this proof? Can I use a yes certificate to solve this problem efficiently? Suppose you gave me a yes certificate. Could I use it to solve the problem efficiently by checking that proof? Well, I could test. Sorry, that's running ahead. I could test if -3, -2, 5 is indeed a subset of the input. Okay. If it's not, I say, hey, that was not a subset of the input. You're lying to me. I could then test if it is a subset of the input. I could test by summing up the numbers if they sum to 0. Okay. Then I would have actually checked that proof. And I'd have found, yes, that proof holds. It is a valid proof that the correct answer is yes. Well, okay, I mean, the oracle might lie to me. It might give me a subset that doesn't sum to 0. Heck, it might not even give me a subset. I mean, depending on what you want to assume about your oracle, it might give you things that don't even look like your input. It doesn't even give you numbers or an array. It could give you completely arbitrary data. But can I check the proof that it gives? Whatever the proof is, can I check the proof and see if it's a valid proof that the answer is yes? Well, I can actually check that pretty efficiently. If you give me anything that's not an array, I can tell you you're lying. Okay, so it has to be an array. If you give me an array that's longer than the input, I can tell you you're lying. That can't be a subset of the inputs. That means I only ever need to check an array the size of the input or smaller. And then once I have an array the size of the input or smaller, I can always check, are all the slots integers? Yes? Okay, good. No, you're lying to me. If all the slots are integers, is this a subset of the input? No, you're lying to me. Yes, keep going. Okay, do all of these elements sum to 0? No, you're lying to me. Yes? Okay, good. Can I do this in polynomial time in the input size? Well, it turns out I can, because all of those checks that I just described, they're going to be at most a polynomial in the input size. So I can check whether something's a subset. Even inefficiently, I can check whether the certificate is a subset of the input in size of the certificate capped at n, where n is the number of integers in the input, because I don't need to check any certificates bigger than n. So if I take the certificate size, and cap it at n integers, and then I take the input size, which is n, and I can, even inefficiently, I can compute the subset in n squared time. I can check if the certificate is a subset of the input in n squared time with 2 loops. I'll show you how later. Okay, so I can check that in n squared time, which is polynomial in the input size of n. Okay. I can sum up these numbers in order n time, which is polynomial in the input size. I can check if it's an array in constant time. I can check if its length is n, depending on the sort of expressivity of your model of your programming language. You can do it in order n time, or you can do it constant time. Doesn't matter. This is all polynomial in the input size. So if I'm given a certificate, I can check whether you're telling the truth, and I now have a proof that the output is yes. I can check that in polynomial time, or I can figure out that you're lying in polynomial time. Okay? So if I can do that in polynomial time, I've written something called a polynomial time certificate verification algorithm. I've verified your certificate in polynomial time. Okay, so let's get into the sort of formalism here a little bit. So a certificate is is what? Well, a certificate for a yes instance, remember an input for which the correct answer is yes, is some extra information C, which makes it easy to verify that I is a yes instance. So for example, for subset sum, you could give a subset that you claim sums to 0. So that would be C, the certificate. Now, what's a certificate verification algorithm? Suppose ver is an algorithm that verifies certificates for yes instances. Okay? What does that mean? Well, ver, it takes two inputs, I and C. I is the input to the problem, so the whole array that we're taking the subset of. C is the certificate, and it outputs yes if I is a yes instance, if yes is the correct answer. So I can check, I can prove the answer is yes, and I can return true, right? And then I should also verify C is a valid certificate, right? It is actually an array of numbers, and it is a subset, right? So I can verify all those things. I should output yes if I is a yes instance, and C is a valid certificate that proves that. Then I should output yes. And if ver IC outputs no, then either I really is a no instance, and somehow the certificate proved to us that no is the correct answer, or I is a yes instance, and C is just a bogus certificate, right? If you give us a bogus certificate, what we're really doing is we're just verifying your certificate. We're not trying to answer correctly, the correct answer for the whole program, right? At least not at our first stab at this. The verification of a certificate is just supposed to say, is this a proof that the answer is yes? Okay? So if we got an invalid certificate, then the answer can be no. Okay? So if the answer is no, then either it's a correct certificate and it proved the answer is no, or we returned no even though it's a yes instance. But what we're saying is that's an invalid instance. No, we can't prove the answer is yes, right? So either we prove the answer is yes by analyzing the valid certificate and we output yes, or we can't prove the answer is yes and we output no. Okay? Okay, and what makes this certificate verification algorithm polytime? Well, it means that it has complexity O of n to the k, where n is the number of bits to write down the input, and k is a positive integer. So it's a polynomial in the size of the input, okay? The number of bits needed to write down the input. Okay, so we've sort of to cast this into the terms that we saw with subset sum. What's ver of I comma c? Well, a correct ver of I comma c should return yes only if C is a subset of the input and the sum is 0, okay? And otherwise it should output no, okay? And it can actually be kind of hard, I should note. This is something fundamental about certificates that's important to understand. It's usually not too hard to express what it means for a certificate to be a yes certificate, for it to prove that the answer is yes. I can give you a certificate that proves the answer is yes without too much work. Meaning I can define what it means for a certificate to imply, to prove that the answer is yes. I can define what it means for a certificate to prove the answer is yes without too much work. Computing a certificate computationally is hard, but I can usually define what it means for a certificate to prove the answer is yes without thinking too hard. But it's often very hard to define what it would look like for a certificate to prove the answer is no. Like, how would I create a certificate that proves no subset of this array sums to 0? I mean, I could give you a huge certificate that sort of shows all the subsets of the array and then claims all of these subsets, they're all of them, and all of them sum to 0. But in order for you to check that certificate, you'd have to kind of go through the entire certificate, which would contain exponentially many subsets. And the size of the certificate would be exponential in the input size, and verifying it would at least require reading the whole certificate. That would take exponential time to verify it, so we couldn't get a polytime certificate verification algorithm to verify that kind of no instance. And could you define a certificate for no instances to prove that instances are no instances without using exponential space and thus exponential time for this subset sum problem? I don't know how. Often it's hard to define certificates for no instances that prove the answer is no. So we usually stick to certificates for yes instances, and we do something sort of careful to make sure that we can always phrase everything we need to prove in terms of yes instances. Okay. All right, so how the heck are these certificates going to actually help us? And I realize this is probably pretty hard for you guys to track because this is a topic that I found students find really, really difficult. This is one of the most difficult topics, I think, for undergrad students to sort of try to tackle in their undergrads. So don't feel bad if this takes a little bit of time. It's going to take repeated exposure and maybe a little bit of a few different attempts at understanding this potentially. So if you aren't completely tracking, don't feel too bad, but really try to pull yourself up by rewatching and asking questions. I'll be happy to answer questions on Piazza about this stuff. It's really important that we do understand it in the end. But if it doesn't all make sense yet, don't feel too bad. Let's keep moving on because we're still in this place where we're feeling things out informally, and I think a bit more explanation will help to make things more clear. At this point, I don't expect you to have any idea how verifying certificates is going to help us at all with defining anything sensible or understanding the complexity of problems. But it turns out it's actually going to help us a lot. So, if we want to solve this subset sum problem, here's a weird algorithm for solving subset sum if we can solve the certificate verification problem for subset sum. Okay, so this is a super weird formulation of a solution for subset sum. Let me take a sip of my tea. Okay, so let's define the type of a certificate for this problem. We'll have it be a set of integers, like an arbitrary set of integers. Suppose I wrote this code. This is extremely inefficient code. Not efficient at all. Okay, we're just going to say for every possible subset of the input, generate that subset. We're going to generate all possible subsets. There are exponentially many subsets, right? Because S is going to be just an element of the power set of X. Now, our verification algorithm is going to be this function sums to 0, okay? So we're just going to sum up all the elements and see if they sum to 0. So what is this algorithm? Generate every possible subset certificate, right? So our certificates will be subsets of X. We're going to generate every possible subset of X, and then for each one, we're just going to verify it. We're going to check that it's valid. We kind of know it's valid, meaning it is a subset of X from how we generated it. And we're going to check if it sums to 0. Now, if any of these certificates sums to 0, it's a yes certificate. It's a proof that the answer to the decision problem is true, so we immediately return true. And a certificate that doesn't sum to 0, it doesn't really prove anything, right? If one of these subsets doesn't sum to 0, that doesn't mean no subset sums to 0. In order to know that no subset sums to 0, we have to see every certificate, right? We have to see that all the certificates sum to a non-zero value. So we don't really learn anything if a certificate doesn't sum to 0. Now this takes exponential time, right? Generating all the certificates is expensive. But verifying a certificate here is actually fast. So the runtime is polynomial in the size of the certificate. How would you verify a certificate? Well, in this case, we actually know something special about the certificates because of how they're generated. We know that they're generated by taking subsets of X. So we don't need to check. It's part of the definition of a certificate here, the type of a certificate, that it's a subset of X. So really, I should have written subsets of the input here. And so we don't actually need to test that whether S is a subset of X. We just test whether S sums to 0, and that's going to help us verify. That's going to verify for us whether S is a yes certificate or whether we learn nothing about it, about the input. Or almost nothing about the input. We only learn if it doesn't sum to 0, we only learn that one possible subset doesn't sum to 0, okay? So how do we do this? Well, I mean, it's just a for loop, right? We loop over the elements. It takes order S time to sum them all up. Order S is polynomial in the size of the input because S is a subset of the input. Okay, so the input to the verify function is I, which is X and S. And so we take the whole input that we're going to verify against, and then we take the certificate as well, S. The runtime is order S. Here's the argument. It's order S. Order cardinality of S is definitely order of size of I, because order of size of I is order of cardinality of X plus cardinality of S, because that's the input to verify, X and S. So this is polytime. Okay, so we've managed to verify certificates in polytime here, but generating the certificates was expensive. Okay, so what is this brute force solution via certificate verifying? What does this have to do with NP, with non-deterministic polytime, the class of problems? Well, we're going to look at, just like we saw, just there on the previous slide, we saw a subset sum solution via generating every possible subset and then verifying those certificates. We're going to see a subset sum algorithm via not generating every possible subset, but a non-deterministic oracle that magically gives you a subset that sums to 0 if one exists. Okay, if there is a subset that sums to 0, this non-deterministic oracle, it's non-deterministic because it has the power to guess. Non-determinism means something like randomness. Okay, so it has the power to kind of flip a coin and guess magically. If there is a subset that sums to 0, this oracle is very powerful. It will, guaranteed, magically return a subset that sums to 0. Now, if there isn't a subset that sums to 0, then the oracle will return anything, any set of integers. Really, it could return any garbage data, but I already explained how if it returns some weird garbage data or some huge data, you would just rule that out with simple checks. So we can assume equivalently, the theory is just as good if we assume that it returns an arbitrary set of integers. Because it would be very easy. If it returns something that wasn't a set of integers, we could just test, is it a set of integers, and be done. We would close the theoretical gap between the powers of those two oracles. Okay, so we're going to suppose there exists a non-deterministic oracle that works in polynomial time in the size of the input, and it magically returns, if there's a subset that sums to 0, it magically returns 1. Otherwise, it returns any set of integers. Okay, so now how do we solve with that oracle as a subroutine? How do we solve subset sum in polytime? Can we solve subset sum in polytime? Well, call the oracle, give it the input, and call oracle. And if there is a subset that sums to 0, the oracle will return it. C will be that input. One of those inputs. One of those subsets that sums to 0. Then we'll call our own verify. Okay, we'll pass the input to check against, and we'll pass the certificate. If there was a subset that sums to 0, C will be such a subset. Okay, and then we need to verify if that certificate is good, if it's valid, if it actually contains a subset that sums to 0. So we'll check if it's not a subset of I, because remember, if there was no subset that sums to 0, then the oracle will just return any set of integers. That might not be a subset of I. So we'll check, is it a subset of I? If it's not a subset of I, we'll return false, right? And we know if we return false, then we'll return false here, right? Verify will return, and we'll return false here. We'll be saying there is no subset that sums to 0. Is that a correct thing for us to return? You could think about that for a moment, perhaps. So it is, because if we return something that's not a subset, okay, if there was a subset that sums to 0, then we will return it. So if we return something that's not a subset, there can't have been a subset that sums to 0. So it's correct for us to return false. Okay? Now, if we get past this line, so C really is a subset of I, then either the oracle really gave us a subset that sums to 0, or it gave us an arbitrary set of integers that happens to be a subset of I. Okay? So if it happens to be a subset of I, well, we should check that it sums to 0. If it sums to 0, then there's a set that sums to 0 that is a subset of I. So we should return true, and we'll return true from the whole problem. And if not, well, we would have returned a subset that summed to 0 if one existed. So since what we found didn't sum to 0, that means there is none. There is no subset that sums to 0. So we should return false. And we do return false, okay? So this actually, given this oracle that satisfies this property, this is a solution, a complete solution, and it's polytime because our verify algorithm is polytime. I argued we can check whether C is a subset of I in polytime in the input, time that's polynomial in the input size, and we can check whether the sum of C is 0 in polytime, and the oracle call is polytime. So this is all polytime. So this is a polytime solution if we assume that there's a non-deterministic polytime oracle. So this means that subset sum is in the complexity class NP, non-deterministic polytime. Okay, so this is all stuff I just said. Okay, so the non-deterministic part is how the oracle magically returns a yes certificate if one exists. And the n in NP is non-deterministic. We have non-deterministic polynomial time. Subset sum is in non-deterministic polytime because if you have access to a non-deterministic polytime oracle that produces a yes certificate if the input is a yes instance, and otherwise returns any garbage certificate. And then, under that assumption that you have that oracle, we can solve the problem using a polytime certificate verification algorithm that we can write that runs in polytime polynomial in the size of the input. Then the problem is in NP. Okay? So let's generalize to any problem, because it turns out you can't just solve subset sum this way. You can solve every decision problem in non-deterministic polytime if you have a polytime non-deterministic oracle and a polytime verify algorithm such that if I is a yes instance, then the oracle returns a yes certificate. In other words, if the correct answer is yes, the oracle returns a proof that the answer is yes. And then your verify algorithm must take a proof that the answer is yes and definitely return true because this was a proof that the correct answer is yes. Now remember, you're taking the input too, so you can check the certificate against the input to establish the real proof that the correct answer is yes. So you should be able to return true in that case. And if I is a no instance, then verify must return false. No matter what certificate the oracle gives you, you must return false because you can take that nonsense garbage certificate it gives you, you can compare it against your input, and you can say that is not a valid proof that the answer is yes. So I return false. In other words, it must be impossible to fool your verify algorithm into returning true. Because remember, verify, its job is to look at the certificate and say, is this a valid proof that the answer is yes? If it's not a valid proof that the answer is yes, you return no, right? So if the correct answer is no, then it should be impossible for the oracle to give you a valid proof that the answer is yes. Right? If the answer is no, it can't give you a proof the answer is yes. So when you compare it, the certificate C against your input, you'll be able to figure out this is not a valid proof that the answer is yes, so I can return false. So if I is a no instance, you must return false, no matter what the certificate is. Okay? So could you fool the subset sum verify function? So think about that for a second if it's not immediately obvious. Okay, the answer is no, because no matter what the certificate is, you're going to check if it's a subset of the input and sums to 0. Could you be fooled into saying yes? Well, if you said yes, you found a subset of the input that sums to 0. It's impossible to be fooled in that case. If you find that, you know the answer is yes. So you're going to return true if the answer is yes. And if you answer yes, it's correct. You should have returned true. Okay, on the flip side, if you are fed a bogus proof, right? You can't be fed a subset that sums to 0 if the answer is no, unless that set of nodes, set of integers that sums to 0 is not a subset of the input. Because if it was a subset of the input, it wouldn't be a no instance. It would be a yes instance. Okay? So here's the algorithm for solving any problem, any decision problem. We take the input, we feed it to the oracle, we get the certificate, this is polytime, and then under the assumption that you have this polytime verify algorithm, you just call it and return whatever the verify algorithm says. And if I is a yes instance, the oracle will return a yes certificate, so you will return true. And if it's a no instance, then verify will return false. So we're going to return the correct answer here in each case. Okay, so for the rest of this course, our definition of NP is not going to explicitly involve non-deterministic oracles, but I like to teach it this way, where I teach you guys the idea that there is a non-deterministic oracle which feeds you the answer if there is a correct one, and if there isn't a correct one, if it's a no instance, then it gives you some garbage, and you check it, okay? Because what we're going to do in the rest of the course is going to be based on certificate verification. I think the certificate verification only makes sense, really, if you think about the existence of an oracle, right? Okay, so just to recap here, what are these oracles doing? Okay, so you have this problem, a very difficult problem, like plugging in a USB drive, okay? You have the oracle and you have the verify procedure. And the oracle guesses the correct solution in O of 1 time, so it does something very, very hard. And the verifier takes polynomial time to decide what just happened and concludes that the oracle actually solved the problem in O of 1 time. Sorry, I said O of 1 time, but actually this is supposed to be poly time. So this is just a glitch in the slides. Okay, so the oracle works in poly time, the verifier verifies the solution in poly time, and then the conclusion happens. And as we're about to see, the existence of an oracle, a polytime non-deterministic oracle, and a polytime verifier, certificate verifier for a problem, means the problem is in non-deterministic polytime. It's solvable with access to a non-deterministic polytime oracle, so it is a non-deterministic polytime problem. Okay, so let's define NP now. Finally, we're in a position to actually define NP, to define non-deterministic polytime. So a decision problem, so NP is only going to contain decision problems. So what does it mean for a decision problem to be in NP or not in NP? Okay, so a decision problem pi is solved by a polytime verify alg. I'm defining the word solved here. It's solved by a polytime verify alg if and only if, for every yes instance I to that problem, there exists a certificate C such that verify I, comma C returns true. There has to be, for every yes instance, and for the way that you defined certificates, because you have to define what your certificates are for your problem type, there has to, for a given yes instance, for every yes instance, there has to be some certificate that proves that the answer is yes. And then you can assume that the non-deterministic oracle will return that certificate if it exists. So if there is a yes instance, there should be some certificate that can prove that the answer to that yes instance is yes. And then your verify algorithm can check whether the certificate represents such a proof that the answer, the correct answer to this instance I is yes, and return true in that case. So for every yes instance I, there should exist a certificate proving that the correct answer is yes, and your verify should, upon receiving that certificate, return true, say the answer is yes. And for every no instance I, verify I should return false no matter what this certificate C is. No matter what garbage you get fed conceptually by the oracle, you're going to check it against I, and you're going to say that's not a valid proof. So for every no instance, verify IC must return false. For every yes instance, there should exist a certificate so that if verify were called on that certificate, it would return true. Okay? So the intuition here is, for a yes instance, there has to be a certificate that verify would accept. And of course, if one exists, the oracle would find it and we would solve the problem. And for a no instance, the oracle can't find any certificate that would fool us. We're going to reject every certificate for a no instance. Okay, this is a crucial, critical definition for the rest of the course. You're going to be asked to show problems are in NP. This is what this means, but we will see an example of showing something is in NP to clarify. Okay, so the complexity class NP denotes the set of all decision problems that can be solved by polytime verify algorithms. I've said here can be solved. There was a post on Piazza about how I defined the complexity class P. I defined it as all the problems that could be solved in polytime. And you can define it, I think, equivalently for the purpose of this course as the set of all problems that have been proved can be solved in polytime. So the distinction is whether a problem that we don't know yet whether it can be done in polytime or not, is it in P, right? And it doesn't make a difference for the purpose of this course. The way that you, regardless of how we define P, the way that you show that something is in P is by showing that there exists a polytime solution to solve it. Similarly, when we define the complexity class NP, I'm defining it here as the set of all problems that could be solved by polytime verify algorithms. I'm defining it this way so even if we don't know for a particular problem whether there is a polytime verify algorithm for it under the non-deterministic oracle assumption, even if we don't know, if somebody really smart could come along down the line and actually show that there is a polytime verify algorithm, we'll consider it to be, the problem itself is in NP. If one day somebody could solve it, like just if it's possible that this problem could be solved, we'll say it's in NP. So this is saying the problem itself fundamentally has some nature. It is in NP or it's not, and it doesn't depend on our state of knowledge about that problem and about whether it's in NP. Okay, the alternative definition is we can define NP as the set of all problems that have been shown to have polytime verify algorithms. Okay? And then something we would say it's in NP only if you have shown, if somebody has shown that there is a polytime verify algorithm that solves the problem. Okay, between these two definitions, it doesn't really make a difference what you pick from the perspective of this course, because we're just going to ask you to show for a problem, show me it's in NP. Okay, and that will mean showing the existence of a polytime verify algorithm. Okay, so when you do that, you will be satisfying both of these definitions of the complexity class NP. So it doesn't matter to me which of those you pick. You can pick the one on the slides, or you can pick the one that was sort of hinted at on Piazza. Okay. Now, you should note this. Separately from what I just said, it's not necessary to be able to actually implement an oracle in polytime for a problem to be NP. We're assuming there is a non-deterministic polytime oracle. You do not need to be able to implement an oracle. There does not need to exist an implementation, a real-world implementation of an oracle in polytime, okay, for a problem to be NP. Really, the oracle is just assumed to exist, and that's it. Okay, we don't need an implementation of the oracle to exist. Okay, keep the following in mind. Finding a certificate, like actually generating a correct certificate, a yes certificate, can be much more difficult. Like, computationally speaking, it can be exponentially more difficult, we think, than verifying that the certificate is a valid proof that the answer is yes. Okay? As a rough analogy, you can think of this as finding a proof for a theorem, which can be much harder than verifying the correctness of someone else's proof. Okay, so let me talk briefly about the mechanics of showing, and I realize I'm going a little bit over time. I'm going to, run up to 90 minutes here, I think, and then I'll cut it off. Please bear with me. We're sort of stretched thin a little bit since we lost these two lectures. Okay, so the mechanics of showing a problem is in NP, because you guys are going to need this for the assignment for A5. So how do you show a problem pi is in NP? Well, first, you define a type of certificates. Okay, for subset sum, let each certificate be an arbitrary set of integers. You design a polytime verify algorithm that takes the input and a certificate as its arguments. So in the subset sum, which I'll use as a running example here, how would I verify an arbitrary set of integers C is a subset of input I with sum 0? Well, I'd sum the elements of C. If they're non-zero, return false. That takes order cardinality of C time. That's polynomial in the input size. Otherwise, I test if C is a subset of I with two loops. Okay, so the pseudocode looks like this. For each x in C, so for each element of the certificate, we're going to find that element in I. Okay, so we're gonna go through all the elements of I and try to find that element. We're going to start out by saying I haven't found it in I. Actually, this line is in the wrong place. This line should be before the for y loop. So we're saying, have we found x over all the choices of y, and we're initializing it to false. That initialization should happen here. For x in I, for x in C, found x equals false. For y in I, if x is y, and we haven't used y already, then used y is true, and found x is true. And if we get through all the choices of y, so basically each element of x, we want to show x as a subset of y. So if there are like 2 copies of 7 in C, We want to show C as a subset of I. So if there are two copies of 7 in C, we want to sort of remember that there should be two copies of 7 in I, right? And so we want to remember which elements of I have we already used to satisfy, finding elements of C. So we have this array of used bits, one for each element of I, and we set that these things are used once we've said, hey, I found X, here's where it is. We've now consumed this location in I. To say this is where we found X, okay? And if we didn't find X at any particular place in I, then we've proved that C is not a subset of I, so we return false. So we do this for each X. For each X, if we fail to find X in Y, maybe because we've already used up all of the 7s and we're trying to find another 7, then we return false. Otherwise, if we find, for every X, we find an unused a copy of that value in Y, then we return true. Okay, and this is two loops. This is done in order C times order cardinality of C times cardinality of Y time. This is certainly polytime in the input. Okay. So we define a type of certificates and a polytime verify algorithm, and then we give a correctness proof. So what's our correctness proof? Well, formally, here's what we're doing. Case 1. Let I be any yes instance. Find some C, okay, so describe, you as the prover should describe some certificate C that will cause verify IC to return true. So what's a certificate that will cause, for my arbitrary instance I, yes instance I, what is a certificate that I can give that will cause verify IC to return true? Well, let I be a yes instance. We know because it's a yes instance, there is a subset that sums to 0. Let C be any such subset. Then, if we provide C to verify IC, we can verify by looking at our code for verify IC that it will return true. Okay, that's it. We've proved this case for subset sum. Case 2, let I be any no instance and C be any old garbage certificate. Prove that verify will return false. Okay, here's example case 2, the proof. Let I be a no instance and C be any certificate. Because I is a no instance, we know there's no subset of I that sums to 0, right? So we know whenever we sum all of the elements of C, it's going to be not 0, okay? Or C is not going to be a subset of I, right? It's going to be impossible for us to find a C that is a subset of I that satisfies sum of C equals 0. Okay, so because that's impossible, because there's no subset of I that sums to 0, and we're going to check the certificate against the input, we're going to return false in every case. Now, this is sort of a difficult proof case, right? Because it's sort of difficult to express the certificates cleanly. It's not really clear what it means. What is a certificate that, in this case? It's some garbage, right? It doesn't really help us. And this case was less elegant to prove than this previous case. So it turns out, if you want to prove case 2 elegantly, usually you end up proving something slightly different. You end up proving something closer to the contrapositive of this statement, and we'll talk about that more clearly next time. All right, well, actually, I think we'll do it here in the Hamiltonian cycle example, which is the next example that I'll conclude with, and then we'll see more details about that next time. Okay, so we've shown here that subset sum is in NP. This is a formal proof that subset sum is in NP. Okay? So let's see one example, and then we'll stop. One more example, we'll stop. So here's another problem, the Hamiltonian cycle problem. Okay, so it's a simpler version of traveling salesperson problem. You have an undirected graph, and you ask, is there a Hamiltonian cycle? A cycle that visits every vertex exactly once, and following some subset of the edges, okay? Okay, so let's show this problem is in NP. So we can solve this problem in polytime if we have a non-deterministic polytime oracle. Okay, so we have to find a polytime verify algorithm. We have to define our certificates. So let's define certificates. Let's do an array of nodes, which it's a sequence of nodes, and the nodes may or may not represent a Hamiltonian cycle. Okay? And of course, if we receive some certificate that's not an array of nodes, we can just test easily. The first check of verify can be, is the certificate an array of nodes? If not, return false. So that's easy. This is not a big restriction saying that the certificates have to be arrays of nodes. This is totally fine. Okay, so how do we verify, given an array of nodes, how would we verify whether those nodes represent a cycle? So you might want to pause and think about that for a moment. And furthermore, how would you verify that the given array represents a Hamiltonian cycle? So you might want to think about that for a moment. Okay, so I'll give you the answers sort of on the next slide as we go. Okay, so a certificate consists, in our case here, of an array of nodes, node names. We'll say the node names are 1 to n, and the array might represent a Hamiltonian cycle, it might not. Okay, this is a verify algorithm where we imagine this is being called on a certificate X that's produced by an oracle. Okay, the oracle gets the graph and the oracle produces a certificate. That's what we're imagining is happening here. This is our verify algorithm. Okay, so we get the graph, this is our input, original input, and this is the certificate that we're checking. Okay, so first thing we'll check, look, if the size of X is not n, because how many nodes should there be on this Hamiltonian cycle? There should be exactly n nodes involved in the Hamiltonian cycle. Each node should appear exactly once in the cycle, n of them. So if the size of X is not n nodes, we return false, okay? And then we're going to say, well, okay, here's how we test if an array is a Hamiltonian cycle. We ask, is it a cycle? Okay, so what does it mean to be a cycle? It means that for each node in the array, there is an edge from that node to the next node in the array. And then for the final node in the array, there is an edge from that final node to the first node in the array, right? So we're going to check that. And then we're also going to check, for it to be a Hamiltonian cycle, if every node in the graph is used exactly once in the cycle. So we'll have this used array to ask, has this node been used already in the cycle? So we'll initialize this used array with one slot per node in the graph to all false. Initially, it's just every cell is false, and then we'll iterate over all the nodes, and we'll iterate over all of the nodes in the certificate. And we'll ask, has the first node of the certificate been used yet? Already. If so, return false. Else, say, okay, we've now used the first node, right? Now, has the second node of the certificate been used already? Yes, then return false. Else, set it to be used, right? If every node in the certificate is used, yeah, that's right. So if all of the nodes in the certificate are brand new when we reach them, they haven't been used yet, that means we don't have any duplicates among the earlier nodes, right? And we should find n unique nodes that haven't been used yet in order for this to be a Hamiltonian cycle that visits every node exactly once. Okay, so this lines 4 to 6, this block of code, tests whether this cycle is Hamiltonian, if it is a cycle. So suppose it's a Hamiltonian cycle, then 4 to 6 will not return false. Now suppose it's a Hamiltonian cycle. I'm building the intuition here, hopefully. I'm not proving it's correct. We'll do that in a second. Okay, so lines 7 and 8, we're going to test if this is a cycle at all. Okay, so we're going to go for I equals 1 up to n minus 1. We'll just test. Is there an edge from xi to xi plus 1? There should be. If there's not, it's not a cycle at all, and we return false. And at the end, we test if there's a cycle from the last, if there's an edge from the last node to the first node, and there has to be, or else we return false, because that would not be a cycle. Okay, if we test all of this stuff, we pass all these tests, my claim is we've found a Hamiltonian cycle, and we can return true, and that's exactly the correct thing to return. Okay, so let's prove correctness. So how do we prove correctness? We have two cases. So if G is a yes instance, where the correct answer is yes to this graph, that we have to say, we as the prover have to show there is a certificate for which this procedure will return true. Okay, well, if G is a yes instance, then there is a Hamiltonian cycle. So, okay, suppose X, the certificate, is a sequence of n consecutive nodes on that cycle. If there is a Hamiltonian cycle, because this is a yes instance, let the certificate be a sequence of n consecutive nodes on that cycle. Okay, so this shows the existence of some certificate for which we will return true, because if we take this certificate X, you could argue fairly easily that walking through this algorithm, we will return true. Okay, so this shows the existence of a certificate for the oracle to find and return to us conceptually, for us to call verify on, for us to discover that it is a valid proof that there's a Hamiltonian cycle in the graph for us to return true, solving the problem. Okay, that's one direction of the proof. That's case one. Case two, if G is a no instance, if there's no Hamiltonian cycle, then every certificate should cause verify to return false. No matter what the certificate is, verify should return false. Okay, now this is sort of hard to prove directly. I think almost always when we prove that things are in NP or are NP complete, we're proving the contrapositive of a statement. What's the contrapositive? Let me tell you. If you have a statement, P implies Q, if P then Q, the contrapositive of that statement is not Q implies not P. If not Q, then not P. Okay, so we're going to do that here. Okay, every certificate should cause verify to return false. If you work out the logical algebra here, the contrapositive is if verify returns true, this is not Q, verify returns true, then not P. What's not every certificate? Oh, sorry, the if is up here. So the Q is every certificate should cause verify to return false. Okay, so what's the negation of this? Some certificate causes verify to return true. So if verify returns true, then what's the negation of the first part? G is a no instance of the problem. G is a yes instance. So if verify returns true, then G is a yes instance. This is the contrapositive of this statement up here. Proving this is equivalent to proving this. But this talks about yes instances, which lets us talk about certificates, which lets us prove things about this problem much more easily. So this is almost always better to talk about the contrapositive of this second case. So we'll prove the contrapositive. So if verify returns true, then G is a yes instance. Let's prove that. If verify returns true, that means it returned down here, right? That means the graph contains a cycle because we established that at lines 7 and 8. And that cycle contains n distinct nodes, which we established at lines 4 to 6. That proves the existence of a Hamiltonian cycle in G, which proves that G is a yes instance. That's a formal proof that this is in NP, that this Hamiltonian cycle verify procedure is a polytime certificate verification procedure for this problem. Okay, well, I didn't argue it was polytime. I argued it was a correct verification procedure. Is it polytime? You can look at this, and it's quite easy to argue to yourself this is polytime, right? This line 2 is constant time. Line 3 is order n, which is definitely polytime in the input. Line 4, n iterations, constant work inside, order n work total. Line 7 and 8 is order n work. Line 9 is constant. Line 10 is constant. All order n. That's definitely polynomial in the input size. So Hamiltonian cycle is in NP. Okay? So let me give this very last slide and we'll conclude. Sorry this is so long. I am going to try to give 3 shorter videos possibly next week, which will not add up to 3 hours to try to sort of offset. Okay, so how are P and NP related? So the last thing I want to mention, so P is a subset of NP. Let me argue this to you quickly. So consider a problem pi in P. I'm going to show that there exists a polytime verify that satisfies these desirable properties to prove that this thing is in NP. Okay, so by definition, because because pi is in P, there is a polytime algorithm to solve pi. Okay, there is no matter which definition of P you like out of the 2 I said, there exists conceptually some polytime algorithm that could, there is such an algorithm either that we know or to be discovered that can solve this problem. That's why the problem's in P. Let's call that algorithm A. How are we going to implement verify I, C? Well, we're going to completely disregard the certificate. It offers us nothing because we can already solve this problem in polytime on every input. So you just take the input and run A on that input. Completely throw away the certificate, ignore it, and we know A of I solves the problem. So regardless of what C is, verify IC is going to solve the problem because we just return the solution that we get from A of I, and A of I solves the problem. Okay, so P is a subset of NP because every problem in P, we just proved, is in NP. Well, how about the opposite? Is NP a subset of P? That would prove that P and NP are the same. This is a $1 million question, literally. This has been studied for, many years, decades now. And we strongly suspect that it's not, but no one's able to prove it, and you can win $1 million. I think it may even be matched to $2 million if you solve this very difficult problem, open problem. So next time we're going to get into polynomial transformations and NP completeness, and we're going to start to look at maybe impossibility results. But here's where I'll stop. Thank you so much for your patience. And I know I've taken some liberties here to run overtime because we're in the online format. I just thought that it would be less jarring to finish the material in one consecutive chunk instead of stopping and then having to kind of like ramp up again in the next video and, recall and introduce background and get you into the same context. So I hope you don't mind this format. As always, feel free to leave any comments on Piazza. And thank you very much for watching, guys.